In this video, you will learn how to solve exact differential equations. So first is, let's consider the first order differential equations in this form. So m of xy dx plus n of xy dy equals 0. So the function m corresponds to dx and the function n corresponds to xy. So how do we solve exact differential equations? So before finding the solution to a given exact dE, we need to test whether that solution or whether that equation is exact. So how do we do that? All we have to do is we get the partial derivative of function m with respect to y, and we also get the partial derivative of function n with respect to x. If these two are equal, then that means the equation is an exact differential equation, and now we can proceed with the calculation and solve for the solution. And to solve for the solution, we use this formula, partial derivative of f with respect to x equals the function m, then partial derivative of f with respect to y equals the function n. And once we get the two f's here, the partial derivatives of those two, we equate them and solve for the final solution. Now let's solve some sample problems. Let's say we're given this problem, 2xy dx plus y squared plus x squared dy equals 0. So let's solve this differential equation. Take note of the first order differential equation form. So this one is our m, function of m of x, y, and this one is in function n of x, y. Now we've already identified functions m and n, then we get the partial derivatives of each of the functions. So we get the partial derivative of m with respect to y first. So partial derivative of function m with respect to y is just the partial derivative of 2xy, because m here is 2xy with respect to y. Since we're dealing here with partial derivatives, and this is with respect to y, so all of the terms other than y will be considered as or treated as constants. Therefore, 2x here is considered a constant. Then we get the derivative of 2xy. So the derivative of 2xy, 2x is a constant, so derivative of y is equal to 1. So this is just 2x times 1, or just simply 2x. Now we already have the partial derivative of function m with respect to y. Then we get the partial derivative of function n with respect to x. So that would be the derivative or partial derivative of y squared plus x squared. Alright, in this case, we are differentiating function n with respect to x. So that means all of the terms other than x are considered constants. So that means y and other terms of variables are constants. So we get the derivative of y squared here, and y squared is a constant, and the derivative of a constant is equal to 0, plus the derivative of x squared, which is just 2x. So this is just equivalent to 2x. Notice here that the partial derivative of m with respect to y is equal to 2x, and the partial derivative of n with respect to x is also equal to 2x. Therefore, these two are equal which means that the differential equation is exact. Since it is exact, now we can solve for the solution. And let me delete this. Now we use this formula, partial derivative of f, where f is the solution to the dE with respect to x, equals the function m of xy. Now m of xy, function m of xy is equivalent to 2xy, so we just have to plug that in here. So that is 2xy. And then we multiply both sides by partial derivative of x, or dx. Then our equation would become partial derivative of f equals 2xy dx. Alright, by the way, this curly funky d here, or partial d, can be pronounced as d or do. So in this case, I will just pronounce this as d. And now we've already separated df and 2xy dx. We can integrate both sides. So the integral of df is f, and then we get the integral of 2xy dx. Again, we're dealing here with partial derivative. So when we integrate this with respect to x, so that means we will only integrate those terms that have x in it, and then we consider the rest of the terms as constants. Therefore, 2xy here is a constant, so we can factor that out. So this would become 2y integral of x dx. Okay, and now the integral of x is just x dx is just x squared over 2 plus c. Alright, so since we are going to solve df with respect to dx and df with respect to y, so we will have two constants here at the end of the solution. So we can use c1 of y, or we can use q of y. So in this case, I will just use q of y. But actually, q of y, c1 of y, whatever notation you will use, it is just the same as the constant c. So it won't be confusing. I will just use a different variable. Now we further simplify this. We cancel out 2 here. So f is just equal to x squared y plus q of y. So now we already have the other solution of a partial derivative of f with respect to x. And now we need to solve for the partial derivative of f with respect to y using the function n of x of y. So let me write this first solution here, so you won't be lost. So this one is for the partial derivative of f with respect to x. Now we solve for the partial derivative of f with respect to y using the function n of x of y. And n of x of y is just this one, y squared plus x squared. And we can multiply both sides by dy, then our equation would become df equals y squared plus x squared dy. And we can now integrate both sides. Now integrating both sides, the integral of df here is just f equals the integral of y squared plus x squared dy. So we can split this because we have addition. So this would become the integral of y squared dy plus the integral of x squared dy. So let me delete this. All right, and since we are dealing with partial derivatives with respect to y, so that means all of the terms, again, all of the terms other than y would be considered as a constant. So that means x squared here is a constant. So we get the integral of y squared dy. This would just be y cubed over 3 plus the integral of a constant, which in this case is x squared, and that would be x squared y plus a constant, the constant c. So we can either use c2 of x, because in this case we are integrating with respect to y, so we use x, or we can use r of x. So this is now our solution. The second solution. Now to solve for the final solution, so we just have to equate the two f's here. So we equate these two. This would become, this is our f1, the first f, that will be x squared plus y, no, x squared y plus q of y equals this one, y cubed over 3 plus x squared y plus r of x. And then we get the final solution. All right, let's simplify this. X squared y here and x squared y here on the right will be cancelled out. So we'll be left with q of y equals y cubed over 3 plus r of x. Now we can solve q of y and r of x by inspection, and we can equate q of y with those terms in the other side of the equation that contains y. So we have y cubed over 3. And then for r of x, we don't have any terms or variables on the left side that contains x. So that means r of x is equal to 0. Now going back to the two f's that we previously solved, this one, f equals x squared y plus q of y, and f equals y cubed over 3 plus x squared y plus r of x. Now we can write the final equation. Actually, f is just equivalent to c, the constant. We substitute back either of the we substitute this one back to either of the two f equations, then we find f equals c. That will be our final answer. So c could be equal to the terms plus q of y, or c equals the terms plus r of x. So let's do that. So we already solved for q q of y is equal to y cubed over 3, while r of x equals 0. Then we can substitute either of these two back to either the two f's that we got. Then it will be the final answer. So that will be f. If we substitute q of y to the first f, so that would be f equals x squared y plus y cubed over 3, or 1/3 over 3. So that will be our solution. Or we can substitute r of x to the second value of f. Then we would still get the same solution. Then our final answer would be c equals x squared. Let me write that down here. c equals x squared y plus 1/3 y cubed. Now let's solve another problem. Alright, let's say we're given 3x times xy minus 2dx plus x cubed plus 2y dy equals 0. First, we identify our m and n. So this is function m of xy, and this one is n of xy. And then we test for the exactness, whether this differential equation is exact. So we get the partial derivative of m with respect to y. So that would be partial derivative of m here. M is 3x times xy minus 2. And again, since we're dealing with partial derivatives, and then we get the partial derivative of this one with respect to y, so that means we will only, all of those terms that have no y in it will be treated or considered as constants. So let's simplify this first. So this would be 3x squared y minus 6x. Alright, so we're differentiating with respect to y, so that means 3x squared here is considered a constant, as well as 6x. Alright, the derivative of y, so we just copy 3x squared, because that one is a constant, and derivative of y is just 1, minus 6x is a constant, and the derivative of a constant is equal to 0. So this is just equivalent to 3x squared. So that is the value, or the result, for partial derivative of m with respect to y. Now we get the partial derivative of n with respect to x. So let me delete this. So we already got the partial derivative of m with respect to y. We now get the partial derivative of n with respect to x. So that would be, okay, n is x cubed plus 2y. So we're differentiating with respect to x, so that means all of the terms other than x would be considered as constants. So derivative of x cubed is just 3x squared, and 2y here is a constant, and the derivative of a constant is equal to 0. So that means this is just equal to 3x squared. Alright, take note here that these two are equal, so that means this differential equation is exact, and now we can solve for the solution. Now we get, using the formula, we get the partial derivative of f with respect to x. This is equal to, or function m of x of y, because function m corresponds to dx. And then we multiply both sides by dx, and we get df equals m of x of y is 3x times xy minus 2 dx. Then we simplify that. We have 3x squared y minus 6x dx. And then we integrate. We integrate both sides. So let me delete this. By integrating both sides, integral of df is just f. And this one, we can split this as the integral of 3x squared y dx minus the integral of 6x dx. Then again, we're dealing with partial derivatives here. So this is with respect to x. So we will only integrate the variables or the terms that have x in it. So the rest of the terms that have no x in it would be considered as a constant. So we can factor out or put outside 3x squared, and this would become the integral of y. I meant y. So we can put y outside, and this would become the integral of 3x squared dx minus integral of 6x dx. I forgot 3. We can also factor out 3. Put 3 out. Alright. And then we have 3y x cubed over 3 minus, and also here we should put 6 outside because 6 is a constant. So this would be x integral of x. So that would be x squared over 2 and plus c. So instead of using plus c, I use q of y, which I previously used in the first problem. Then we can further simplify this. 3 here will cancel out, and then 6 is divisible by 2, so we have 3. Therefore, f is equivalent to x cubed y plus minus 3x squared plus q of y. So this is our first f. Now let's solve for the partial derivative of f with respect to y with the function n of xy, because n here corresponds to dy, and then we multiply both sides by dy, then we get df equals function n dy. Right. And now we have df equals n is x cubed plus 2y dy. And then we integrate both sides. Right. Again, we're dealing here with partial derivatives. So we are integrating here with respect to y. So that means all of the terms that have no y in it will be considered as constants. So integral of df would be f. Then this one we can split as integral of x cubed dy plus integral of 2y dy. We are integrating in terms of y. So x cubed here will be considered as a constant, so we can put that outside. Integral of dy plus 2 integral of y dy. Right. This is our f. Okay. So our f would be x cubed integral of dy is y plus 2 integral of y dy is y squared over 2 plus c. In this case, I use r of x, which is just equivalent to the constant c. So let's simplify this. 2 here cancels out. So our second f would be equivalent to x cubed y plus y squared plus r of x. Now we've already solved for the two f's. The next thing we do is we equate the two f's. So to solve for q of y and r of x, which we will later plug into either of the two f's that we've already solved. So we equate the two f's. That would be x cubed y minus 3x squared plus q of y equals x cubed y plus y squared plus r of x. Alright, so let me delete this so it won't be confusing. Now we already have this. So x cubed y here will cancel out, and then we'll be left with negative 3x squared plus q of y equals y squared plus r of x. By inspection, we can equate q of y with all of the terms in the right side that have y in it. So that would be y squared. And then for r of x, we equate this with all of the terms that have x in it. So this would be equal to negative 3x squared. Now we already have the values for q of y and r of x. We can plug in either of these two to either of the two f's that we previously solved. So let me write down the two f's that we previously solved. Okay, now you can choose whichever of these two you would plug into either of the two f's here. So if you were going to plug in q of y to the first f, so this would become f equals x cubed y minus 3x squared plus y squared, and this is just equivalent to c, the constant. So this is the final answer. Or if you're going to plug in r of x to the second f that we solved, this would become f equals x cubed y plus y squared minus 3x squared equals c. So basically they are just equivalent, and this is our final answer.